Welcome back, everybody. We are continuing with our Chapter 8 notes on subsidence and soils, and this is the beginning of Section 2 of Chapter 8. Now, in the first section, we talked about what soil is and what it contains and kind of some of the properties that it has and how it's classified. Now, in Section 2 right here, we're going to be talking about what soil does. I mean, we know that soil can help plants to grow, but I mean physically what soil does to create what we would call natural disasters or some sort of hazards that affect us. Soil can change its volume because of what it is, because of what it is made of. It is made of all kinds of organisms. It's made of partially water and rock, and all these different factors can fluctuate in volume because of how it reacts to things around it. So, part of the name of this chapter is in fact subsidence. And that is really just ground failure, or the depressing of the ground because of a variety of different things. First of all, this word dissolution right here, that's just the noun form of dissolve. You know what dissolve means. And so rocks can actually dissolve underneath the surface. And so if that happens, your surface is a lot less stable than it previously was. We call that karst topography. We're going to talk about that a little bit later on. The ground can thaw. All right, it's frozen, then it thaws. You know that ice and water are different volumes. Ice actually swells up and water contracts, or when ice melts, it contracts into water. So that can change the volume of the ground. Sediment itself can compact. It can settle down and change the volume of the ground. And also even earthquakes and even magma draining out from under the ground can cause the volume of the soil to change as well. So in many cases, these are natural processes that cause this, cause the soil volume to change. And like I said before, when water goes from liquid to solid and back to liquid again, it can heave up and down because of the change in volume. So this happens on a small scale and isn't necessarily life-threatening, but it can cause some hazards that can affect maybe the ground that your house is built on or other things. So we're going to be talking a little bit about those factors in this section of the chapter. All right, so the first thing we're going to be talking about is what's called karst or karst topography. I'm actually not even sure where that name comes from, not even sure if it's a foreign word or even named after somebody, but karst topography is really where you have rocks that are dissolved underground and therefore causing the surface to depress and create indentations. Now I'll show you some pictures of this, and we're going to talk about this in a little more detail so it'll make a little bit more sense. But you have types of rocks, especially those that are called evaporites. All right, that is rocks that that are caused by evaporation. Now, we didn't spend much time talking about the way sedimentary rocks are formed, but some sedimentary rocks underground are caused by water evaporating. For example, rock salt. You know that salt is left behind after ocean water evaporates, right? You probably experienced that at the beach. Also, gypsum. Gypsum is another rock or mineral that is left behind, very much like rock salt. Okay, so when that water evaporates, they're left behind. But it also means that they can easily dissolve as well. So rock salt, as easily as it is left behind after you come out of the ocean, it can just as easily be dissolved back into water later on. But the one we're going to be talking about the most is called carbonates. You've probably heard of limestone. Right? Limestone is a very common rock around here. It can be a variety of colors. Very often it's grayish or whitish. But rocks that are made of carbonates, very much like limestone, are dissolved by acidic water. And it doesn't take much for water to become acidic. If you have carbon dioxide that dissolves in water, it all of a sudden becomes slightly acidic. And so I'm going to show you kind of some of the factors that contribute to some of these rocks underground becoming acidified and therefore dissolving. First of all, let me show you one or two places that exhibit what's called karst topography. All right, this place right here is the middle of southern Florida. All right, now what you see right here in southern Florida is a series of lakes lots and lots of lakes, hundreds of them, possibly even thousands of them, all around through southern Florida, or well, middle Florida. This lake right here, you only see a little bit of it. I think it's called a Lake Okeechobee, and all these other ones that are kind of speckled throughout the middle of the peninsula right here are lakes that are caused by the ground subsiding and sinking in. You may have heard of sinkholes happening in places like Florida. And when sinkholes take place, water eventually fills in and creates what looks like a lake. Another very common place is known to be in southern Minnesota. Now, we don't see the whole state right here, but it kind of goes up and off the top of the picture here. But this is southern Minnesota, and you can see the city of Minneapolis right here. And you probably know that Minnesota has a nickname of being the land of 1,000 lakes. Look at all these lakes in here, and especially southeastern Minnesota. The lakes are caused by what we call karst topography. Some of upper Minnesota, it's possible that the lakes were formed by glaciers, but southeastern Minnesota, karst topography, that is rocks underground dissolving and creating caverns and collapsing in and creating sinkholes that fill with water, is what causes a lot of these lakes right here. In fact, you may have heard of this sports team now. There we are. The Lakers, right? Of course, they're in Los Angeles, but you would think, wow, where did they get their name? Well, they actually used to be in Minnesota before they moved to Los Angeles. So the Lakers retained that name, even though their name harkens back to them being up in Minnesota. All right, so this right here is what you would see if you saw an area with karst topography. You see all these sinkholes right here, or these depressions in the ground. Well, if they're deep enough, they can fill with water, and we see those as lakes. All right, so back to our slide here for a second, our original slide. All right, so what causes all these depressions? Well, when rocks that are made of either evaporites or carbonates, when they dissolve underground, they leave behind caverns. If you've got a cavern underground that, let's say, your home or some other building is sitting on, it can very easily sink in and cause what we call a sinkhole. So we can see either pits near the surface or possibly even lakes that are caused by water filling in these depressions right here. So a karst area or a karst plain just shows a whole variety of that either depressions or actual lakes that have sunk in. All right, so it happens kind of like this, where you have water underground flowing right here. Okay, and that water is slightly acidic, and that slightly acidic water reacts with the carbonate or evaporite rocks that are underground, and so all of a sudden you have them being dissolved away, creating these caverns here and here and here. Well, eventually at some point, those caverns collapse because of pressure from the surface, and so you have all these pits now all over the surface of the ground right there, and that's what we call karst topography. So let's think for a second right here. What causes that? Well, these let me go back for a second. These carbonate rocks. What chemical makes up carbonates? Well, carbonate is a chemical compound that we call CO3. All right, and anything with a CO3 attached to the end we call a carbonate. Well, one good example of a carbonate is a compound called baking soda. All right, in fact, it used to be called bicarbonate of soda. Okay, the soda part comes from the fact that it is actually NaHCO3. All right, if you know what Na is sodium. So oftentimes we call it sodium bicarbonate. Okay, and so the fact that it has this carbonate attachment on the end means that anything with carbonate will react with an acid. What's a common acid that we mix with baking soda? That is vinegar, right? We mix vinegar with baking soda and we get all wonderful reactions right here where we can simulate supposedly volcanoes, right? Of course, we know that volcanoes really have nothing to do with the reaction of baking soda and vinegar, but we get this foamy stuff and we all cheer because it froths up much like lava or magma does. But really what's happening is this. All right, so you have just vinegar right here. You add baking soda to it, And well, that foamy reaction takes place, but that solid baking soda, that white powder, it goes from being a powder to dissolving away. And so as a result, a lot of that dissolves away and turns into a gas that you see. What's happening right here? Well, it's inflating the balloon. So when you add, let me go back a second. When you take that acid, which is, in this case, vinegar, a pretty weak acid, and you add that carbonate to it, the carbonate dissolves away, turns into a gas, and we have that reaction. But what happens is that the key thing here is that that carbonate, that solid, dissolves away. That's what's causing all these caverns underneath ground surface. And the caverns are what present this. All right, so those caverns create sinkholes. Right, you can have a surface of the earth that seems perfectly solid, but not far below the surface it may be a cavern forming. And as it collapses, all of a sudden now you have no longer a solid surface, but you have a sinkhole. All right, and so if your house falls into it, that presents itself with a problem. All right, so two different kinds of sinkholes that can happen right here. Well, they can form because of, like I said before, acidic groundwater. You know, very much like vinegar flowing through and dissolving through fractures and joints in the rock right there. And wherever there is a hole underground, water is kind of drawn to it because water wants to sink to the lowest level. So water is drawn into these cracks and these fractures and these joints, and so it just exacerbates the problem. All right, so a sinkhole can cause by solutions dissolving out rock. You could also just have a sinkhole happen because of a cavern underground becoming weak and the ceiling of it collapsing in. So I guess you could say a cavern sinkhole could be caused by a solution sinkhole, that is the water dissolving out rock. But either way, it happens. All right, so you have these areas right here where water is able to flow through, and as it flows through cracks, it dissolves out more and more and more of that rock, because especially if it's carbonate rock, slightly acidic water will dissolve that out. And if this cavern right here gets too big, the surface or the ceiling of the cavern will collapse in, and that's what we call a sink. All right, so a cavern is really another name for a large cave. And so you may have been to caves before and seen all these features and probably asked yourself, why is this cave even here? Why am I underground, and yet why do I have a place to walk right here? Well, it's because this area was dissolved out. All right, dissolution is the noun form of that. So wherever water flows through, it dissolves it out, and if the water flows on and drains out, now all of a sudden you have an empty cavern right there. So all this dissolving of water and depositing of minerals like carbonates and limestone, it can cause some cool formations. Flowstone is one of them. We're not as familiar with that, but you probably are familiar with stalagmites. Those are these spikes coming up from the bottom caused by water dripping and building up kind of a tower. But also stalactites as well. These are stalactites coming down from the top, where that water filled with dissolved carbonates drips down, and then the water drips off and leaves a tiny bit of mineral and rock on the end right there. So these things, these stalactites and stalagmites, are actually rock, but it's that carbonate rock that is being dissolved and deposited, that makes all these formations right here. You can also have formations occur at the surface as well. You can have things called tower karst, which are actually pretty cool looking. The next picture I'll show you is going to be an example of tower karst. China, southeastern China, is famous for this. But here you have limestone on the Earth's surface that have been carved or dissolved into interesting formations by acid rain in the air. Now, we know China is famous for having very poor pollution regulations, and so China has a very bad acid rain problem. So acid rain can dissolve away limestone and create interesting towers. In fact, here, I'll show it to you. All right, so these are karst towers right here. These limestone towers that are dissolved away. Really kind of cool looking, but it is really the shaping of Earth's surface as a result of acid rain affecting limestone. How else can you see karst topography at the surface? Well, sometimes streams can just simply disappear. streams on Earth's surface that suddenly disappear because of you've got joints or fractures that the water just flows right into, and so all of a sudden you get this stream flowing down into the ground somewhere. Likewise, you can have a place where a cave opening is open to the surface, and so water flowing through it can actually flow out onto the surface as well, and we call that a spring. So kind of a spring and a disappearing stream are kind of two opposites of the same coin. So these are all ways that the karst topography can be exhibited at Earth's surface. I showed you this picture already. All right, and there are also places where karst topography can take place, not necessarily because of dissolving of carbonates underground, but because of the changes in temperature. Thermo, you probably know, means temperature, and so this is karst topography that results that takes place as a result of permafrost. All right, now, permafrost is one of your vocab terms, and that's areas that are permanently or almost always permanently frozen. That is, the ground is frozen because it's at a high latitude. All right, frozen all year round. Every now and then, though, it can thaw. I guess that kind of defeats the name of permafrost. So if it thaws eventually, it's not permanently frozen. But if it's mostly frozen, but then it thaws every now and then. Well, thawing, ice turning into water. You know, the ice expands and water contracts, and so when it turns into water, it can actually cause land subsidence because that frozen ground contracts. All right, and so when you see the soil that is kind of fluctuating up and down a little bit, not very even, we call that thermokarst. You might even see maybe in your garden at home or your parents' garden, if you see things like mulch getting frozen. And then when it contracts, when it thaws, it creates all kinds of weird formations in your garden. I noticed in my garden that the mulch is especially famous for that. That's kind of an example of thermokarst. So all those were examples of karst topography. That is the Earth's surface heaving up and down or collapsing because of caverns being formed underground. Now we're into the area of sediment and soil compaction. Sediment, when you remove water from it, collapses. All right, you've probably seen pictures of a really dry desert pavement with all those cracks in it, right? Well, if you have, that's caused because of the water, leaving the soil. There's no water, and so the sediment really compacts down. So if it contracts so much, it'll create those cracks. River deltas, you might see that happening because there's a lot of sediment, a lot of fine sediment there. And so as flooding takes place, as you might have a river, we talked about floods a couple chapters ago, overflowing its banks, sediment that is contracted won't contract too much because the flooding replenishes the sediment and also adds water to it, and so the collapse doesn't really take place. But certain soils can be what we call collapsible. Any place you have soils that have components such as dust, all right, or loess. We talked about how loess is kind of like a fine sandy soil, or stream deposits, much like sediment, especially in regions that are arid or dry, can cause soil to collapse. That is, to break apart and not really hold together. I'm sorry, I need to go back and modify what I said right there. I'm still thinking of sediment. When you have collapsible soils, like dust deposits and loess and things like that, loess being kind of sandy soil, sometimes you can have minerals that hold them together. All right, they will stay together because of minerals that are kind of in between those particles. All right, but sometimes, unlike sediment, that shrinks when water leaves it, sometimes when you have collapsible soils, when water is added to them, some of those bonding minerals, like little teeny tiny particles that hold the particles together, if those particles in between are water soluble, they'll get carried away, and therefore the soil itself will collapse and will no longer hold together. So that's what a collapsible soil is. Not as much like a sediment that collapses when you remove water, but rather when you add water to a collapsible soil, that's when it actually gets carried away and becomes almost like liquefied because it can't hold together. You also probably know that organisms, when organisms die and decompose, when they dry out, they tend to shrink and contract. Well, many places that have lots of organic matter in it, much like wetlands, all right, you've got decaying plant and animal matter. If they dry out, or if the water is drained, the soils can collapse as well because you have a lot of that organic matter contracting and shrinking when water leaves it. So these are all various different ways in which soil can compact, not because of karst processes, but because of water being added or removed from that soil. We know it's also true from previous chapters that when you have tectonic processes taking place, whether it's earthquakes or volcanoes, but especially earthquakes can cause uplifting or subsidence of the ground as well. We have right here a fault taking place, right here, a thrust fault, right? Where you have this plate subducting and taking this plate overlying right here and bending it, and then when it finally returns to its original position, that's what we experience as an earthquake, but it also causes the land up here to rise and then and then to fall down. So even earthquakes can cause land subsidence after the earthquake occurs. Volcanoes are another instigator, you might say, of subsidence of land. Magma can flow for dozens or even hundreds of miles underground. And so when a volcano is erupting, you don't always see the lava flowing like down the sides of the slope, but a lot of times it'll flow through tubes underground. In fact, we call them lava tubes. So when those tubes carry the molten lava or magma out towards the ocean or towards lower elevations, that's great. But at some point, if that eruption stops taking place, those tubes can drain out. And so close to the surface, you can have this underground tunnel or tube that is vacated or empty, and it can cause the land to subside, especially if that tube collapses. So after the lava or magma is done flowing, the surface can subside as well because of the collapsing of that lava or magma tube. So we talked about how some soils, like collapsible soils, collapsible soils and sediment soils, if you add water to them, add or remove water to them, they'll either contract or they'll get washed away or carried away. We also have things that are just called expansive soils, and we know that soil expands because when it freezes, that was like a thermokarst, right? When soil freezes, it expands, and when it thaws, it contracts. But even just adding water, so wet and dry periods, can cause shrinks to kind of heave up and down. Clay and shale, all right? Now, shale is a type of sedimentary rock, but we know that clay is one of our soil sediment types, right? Very, very fine, very, very fine material. And so when you have water added to it, it can crack it can expand and crack, and then when water is removed, it can contract again. So after this takes place, you have these weird cracks and almost like a popcorn type texture that occurs in the soil. One thing I didn't mention here, smectite is kind of it's a mineral that has properties that cause it to shrink or to expand or contract depending on if it's wet or dry. All right, and so the surface, as a result, where we live, will result in kind of wavy bumps. All right, we can see sidewalks sometimes cracking as a result of expansive soils. Unfortunately, sometimes the foundation of your house can experience that contraction or expanding as well. Utility poles, we know that happens sometimes as a result of creep, right, which is a mass wasting event, but also it can occur because of expansive soils, but also headstones too. In fact, when I was in Boy Scouts, my Eagle Scout project involved, among other things, writing headstones in the nearby cemetery because they had fallen over, possibly even because of expansive soils. Soil does move, and so if you have a very old headstone that people don't take care of, it can bend. I'm sorry, it can not bend, but hopefully not. It can lean or tilt because the soil underneath it is changing its volume. All right, so right here is an example of what could happen if you have an expansive soil. Right, so if you add water to it, the water can seep in between the particles of the plates. That is the mineral plates, whether it's clay or smectite, and it can expand. All right. Well, if the water leaves or if it becomes dry, it can contract again, and so your house or trees or headstones or whatever the case may be, utility poles can shrink or bend depending on how the surface reacts to that expansive soil. All right. So we talked about how when soil contracts, many times we see these cracks taking place right here. Look at this. This is C. We'll go to B right here. Look at the sidewalk right here. All right, probably wasn't formed like that. Sidewalks, when they pour concrete, they like it to be in straight lines, so it was probably poured in straight lines. But as the soil expanded and contracted, we see that evidence of that at the surface. And also this poor person's concrete driveway, which concrete driveways, as I understand, are supposed to be more durable. But if you have the soil underneath, the soil can really wreak havoc on that and cause the driveway to crack as well. And even though I mentioned this already, we'll just go into a little more detail right now. Frost-susceptible soils. These are soils that have just the right types of soil grains, like silt-sized, to actually cause heaving and bending of the soil surface as a result of freezing and thawing. We know that when water freezes, it expands, and so it moves the soil upwards. And that's what we call frost heaving. And so 3 conditions, some of them actually seem kind of common sense. First of all, you need to have water present. All right, you can't have frost-susceptible soils if you don't have water, if you have a very dry climate. Obviously, you need to have water. You also need to have freezing taking place. All right, temperatures need to be low enough for long enough to allow the water to form ice. And of course, when ice forms from water, it expands. It's very unique. It's a very unique property of water that it expands. Most things, when they get cold, when they solidify, they shrink. But water does not. Water expands. And so you need enough silt-sized particles in the dirt or the soil to allow water to kind of percolate through. All right, silt-sized has just enough gaps in between for water to seep through. If it's too much smaller than silt-sized, water can't penetrate it enough, and so you won't really have this frost-susceptible frost heaving taking place. You'll just have cold soil. All right, so the next picture is what you might see as a result of frost heaving. Okay, the soil on the surface here just having buckled upwards because water that was in the soil froze and therefore expanded, and so you have this kind of uneven surface on the soil. So those are all a series of different processes that cause the soil, that is Earth's surface, to become irregular. Especially remember karst topography and thermokarst, but also the other things as well, such as frost-susceptible soil and expansive soils, and soils that if you add or subtract water, they change their So changing of the volume of the Earth's surface, especially underground, is what causes problems for us on the surface, because the Earth's surface, it changes shape accordingly to that. So that is section 2. Thank you for following along with me this whole time. If you have any questions, please ask me. But in the meantime, thanks for watching, and I'll see you on the next one.